In this video, I will present a solution to Baltic Way 2022 problem 17. Firstly, we'll have a look at the statement. We consider a positive integer n such that the sum of its positive divisors is at least 2022 times n. We shall prove that n has at least 2022 distinct prime factors. This problem is concerned with divisors and prime factors of n. Therefore, our first step is to define the prime factorization of n. So, let n be equal to p1 to the power of x1 times p2 to the power of x2 up to pm to the power of xn, where p1 is less than p2 up to pm are prime divisors. So xi is supposed to be at least 1. We want to use this representation to get information about the divisors of n that we are interested in. And we can note that if some number d divides n, then d is equal to p1 to the power of y1 times p2 to the power of y2 times pm to the power of ym, because d cannot have any other prime divisor besides those numbers pi. And additionally, we need that 0 is less than or equal to yi, which is in turn less than or equal to xi. So we know if d divides n, then d can only be divisible by these primes, and the multiplicity of how often pi divides di, which we define to be equal to yi, is at the most xi. Furthermore, we note that if some number d is of this form, then it obviously also divides n. So this is an equivalence relationship. Now we have found a way to characterize the divisors of n in terms of its prime factorization. Originally, we are interested in the sum of the divisors of n, which we know to be equal to at least 2022n if we sum up the positive divisors of n. So let's note down this given inequality. We know that 2022n is less than or equal to the sum of d dividing n, where d is positive, of d. Using what we have found in the previous line, we can rewrite this sum to be equal to the sum of all p1 to the power of y1 times p2 to the power of y2 up to pm to the power of ym. And now we have to define what intervals those yi range over. So 0 is less than or equal to y1 is less than or equal to x1. 0 is less than or equal to y2, which is less than or equal to x2. And 0 is less than or equal to ym, which is also less than or equal to xn. We see that this sum has very many summands, because we are ranging over all of the yi simultaneously. Because of this form, we can rewrite it in a really nice way, because this is exactly equal to the product of y going from 1 to m, and we're going to multiply many sums which are exactly equal to this large sum, and this inner sum is equal to the sum of yi lying between 0 and xi of pi to the power of yi. Now it is clear that both sides are equal, because we can convince ourselves that there exists a bijection between all of the summands on the left and on the right side. So we can, if we start with the summand right here, then we have chosen all of these y1, y2 up to ym, and if we choose the exact same y1, y2 up to ym on the right side and multiply this out, then we get the same summand, and this always works left to right and right to left. This is a geometric sum. Therefore, all of that is equal to the product going from y equal to 1 up to m of pi to the power of xi plus 1, one more than the last term in the exponent, minus 1 divided by pi minus 1. That is about as nice of a representation that we can get for the sum of positive divisors of n in terms of its prime factorization. We also have a representation of n in terms of the pi and xi, which is really nice. We want to bring all of those variables to the right side, and then we are going to be left with an integer 2022 on the left. So we get that 2022 is less than or equal to the sum of positive divisors of n divided by n. By what we found here and the definition of the prime factorization, this is equal to the product of I going from 1 to n of pi to the power of xi plus 1 minus 1 divided by pi minus 1, all divided by the ith factor of this prime factorization, which is equal to pi to the power of xi. This equals the product of I going from 1 to n of pi minus pi to the power of negative xi divided by pi minus 1. We are interested in bounding m, the number of distinct prime factors of n, from below by 2022. We already have a 2022 on the left side of this inequality, so we would like to be able to say something like, well, this is just less than or equal to m, and in this case we would be done. We don't have much information about these exponents xi, but we do know that if xi gets really large, then minus pi to the power of minus xi is going to go to 0 from below. And therefore, one estimation is just to say that, well, since each of those summands is less than 0, all of this is less than or equal to the product of I going from 1 to n of pi divided by pi minus 1, which is now a really simple product just in terms of those prime factors. This really looks like a telescoping product. The only problem being that those are primes which are not consecutive integers. If all of these primes were consecutive integers, then all of those numerators and denominators, except for in the first and last term, would cancel out, which is really nice. But we can get some bound like this on those prime numbers, because we know that, well, p1 is a prime number and therefore is at least 2. Now p2 is greater than p1, which is 2, so p2 is at least 3. And by continuing this process, we can say that pi is at least I plus 1. Furthermore, the function x divided by x minus 1 is decreasing. Therefore, if we plug in lower bounds for the pi, then we will get an upper bound for this product. So this is less than or equal to the product from I equal to 1 up to n of I plus 1 divided by I. But this is, as I've described before, nothing but n plus 1. All in all, we get that n plus 1 is greater than, because in this case we don't have inequality at all, n plus 1 is greater than 2022. Therefore, 2021 is less than m, which implies m is at least 2022. That is exactly what we wanted to prove, and therefore we are done.